it's my pleasure to introduce Josef. Maybe no need for long introduction of Josef in this place yet. So Josef is a distinguished researcher at CIIRC here in Prague. He's also on a leave of absence from Inria in Paris, and we miss him. But he has a longer collaboration with these guys. He's also the head of the ELIS unit in Prague, among other things. And the last thing I will mention, because I did it with Cordelia, with the test of time prices, you also have 3 of them, 1 at CVPR and 2 at ICCV. So we are in good company today. And the floor is yours.
Thank you very much, Patrick, for a nice introduction. I understand we are late, so I try to be shorter than this. Yet I would like to tell you a little bit what I'm excited about currently in my research. And so I'll start with this video, and hopefully it will start playing. So imagine now you are in a car and you get a flat tire, and you're far from getting help, yet you have a reception, so you can Google up and say, well, how do I change a car tire? We have a spare replacement. And this video comes up where someone is showing to you actually how to, what manipulation actions you need to do, narrated with natural language, explaining you what you need to do to change the car tire. And in fact, if you don't like that video, there are other videos with different tools, slightly different tools and maybe different car models, which show you how to do the specific task of changing car tire. In fact, there are millions of these videos for different tasks in different domains, going from car repair, gardening, cooking, or healthcare even. So really these instructional videos provide a very nice sort of test bed for learning from visual content together with natural language, because they are narrated, people explaining what they are doing on the video. And so we've been looking at this domain now for a while, and one of the sort of overarching goals would be, what if we could actually learn from this data, some kind of an instructional manual which we can then go and apply in different contexts, for example, in augmented reality. Imagine that you can now automatically give instructions to a novice user how to do a specific task in a new environment, both maybe for home repair, but also actually this is in industry, you have often tasks which are automated, workers doing that, and you want to maybe at least check them. Have they completed all the steps in a particular assembly task? Another example is robotics. Imagine then the robot can go in and look at at some of the instructional videos and learn a new task and then do the task in a new environment, maybe because a person cannot go in that environment. So these are some of the applications which we would like to do, and I will show you some of the works we've been doing in the past few years in that area. And I will try to really sort of watch the time so it's not too long. So the first one is really learning from video and language. It was one of the first works we did in that was actually identifying the individual steps of the task. So on the right here, you saw the automatically learned steps from the narration and the video, and on the bottom, actual temporal localization of these individual steps in the video. Yet these results was interesting. We could actually identify the different steps, but they were relatively small scale. These were learned from maybe on order of 50 videos of a particular task of changing car tire. We were doing maybe 5 to 10 tasks, so relatively small scale. So one of the next steps afterwards were, can we really take this large scale? So we've downloaded and still one of the largest available video data set. Cordelia mentioned it here, it's called How to 100 Million, where we took on the internet, you can actually download instructions for many different tasks on the WikiHow. And we took more than, I think, 10,000 different tasks and obtained more than 1 million videos for different for these different tasks. And in the end, have more than 100 million clips. And what the goal here is now to learn a joint video and language model. So you see there is a video and language from these videos. So without any specific manual annotation, the model tries to predict for a given video the actual text narration. So you see at the bottom, it's learned with a contrastive loss. So it tries to also the narrations from videos which are from different videos in that joint embedding space. It's trying to push them apart. And this actually works quite well And then I'll just show you examples of what you can do with this. You can then do, so you can now search in language, type glue, and it will find you other videos where people are gluing. And this is not using the language at all, the narration, just based on visual search, given the language embedding. But you type glue wood, and it will find you examples of videos where people are gluing wood, cut wood, or people are cutting wood. You can even be more, so here we'll see cut paper. You get video where people are cutting paper. You can be even more specific. You can put cut paper in circle, and you will get videos of people cutting paper in circle. And so what's exciting about this is that we used to have to manually annotate different videos with different the labels, but here the natural language provides almost infinite label space because it's compositional, and you can search for any sort of composition of the given by the natural language. And in fact, and I will skip the details of the evaluation, but really given the large scale of the data set, it sort of can outperform models trained on manual annotation. So we've been, as a community, but also have been working on these sort of weakly supervised learning models from readily available data for quite a long time. And now we are seeing that these models can outperform manual annotations. So this is all online. You can even do the searches which you've seen. You can try it out yourself. So this was, you can use for other tasks. Cordelia talked about it. I'll skip this. So now we've seen learning from large-scale video and language. But in reality, the world is very, if you want to do physical interactions, the world is you need to go beyond just being able to describe or search videos. So this is an example of work with Nicola Mansart, who talked earlier about extracting from instructional video, which is on the left, and I'll try to play it again. Input video, and on the right is the reconstructed motion of the video, but together with estimated forces shown as yellow arrows between the person on the ground and the interaction with the object. So we can estimate this from the video. It's set up really as a two-stage problem. First, we do estimate the person pose, the contacts, and the tool position in 2D, but then we formulate as an optimization problem where we minimize the reprojection of the video of the sort of 3D estimates into the video, but subject to constraints which are by the contact motion model, full body dynamics, and force model. So, and this is, one can also evaluate this, also validate on a ground truth, but what we're really excited about, the part on the left, which is applying it to instructional videos, where now we can really estimate the interactions in 3D, how people are interacting with objects, and estimate the forces of these interactions. And why is this interesting? Is because then we would like to put this motion on a robot. And this is a more recent work from this year, and this is collaboration with, which I think was shown by Isabelle yesterday, where with Justin Carpentier at the Prairie Institute, where we would like to, given an input video on the left, really use that video to drive a manipulation action on the robot. This is difficult because the action is dynamic, so it's hard to actually learn this automatically by reinforcement learning. But what we do here, we use the instructional video to guide the learning process. We extract the 3D motion using what you saw just before, and then have a new method to align the simulated environments with the sort of input video. And then in the simulated environment, we can perform reinforcement learning and learn actual policy, which can be then run on the robot. And I will sort of skip the details of the method, more show you some of the results. We actually done it for several different tasks and several different input videos. And for each of those, we have an environment in which we can check that we can really learn the particular task, like the shoveling, hammering, or using the side here. One can evaluate, and actually what we can get similar performance to what's called, if you do the demonstration in the robot space. So just by learning the video, from the video, it's like if you were, which is the standard approach in robot programming, if you do it in the robot space. What's interesting is that one can do this, it doesn't really depend because it's focused on the tool, on the morphology of the robot. So we can learn these policies for robots with different degrees of freedom or very different morphology, and it's still, one can sort of learn from these instructional videos even if these are not humanoids. And it works similarly for different morphologies. And finally, what I would like to mention is, so in the end, still the policy which we learned was open loop. So we really learned it from the video and then transferred it on the robot, but there was no perception. So we would like to really now close the loop, and that's subject of the future collaboration which we have with Nicolas Mansart and also Justin Carpentier in Paris and Toulouse, on really having now closing the loop and having robots observe the environments and sort of learning how to act on them with the perception. And here is an example of work which we have in this direction, where we would like to really give one or more input images to estimate the pose of the object in 3D in the environment, because here is the example. So in this case, we have a given cut model so that we can manipulate the object by robot. And we've developed an approach which combines deep learning with multi-view geometry, which I'll skip the details, but it works quite well for this task. So we have on the top is input image, middle row is predicted poses, and at the bottom is the 3D visualization given the single input image of the scene. So now it can really go, and robot can manipulate these objects. These are different data sets for a competition on this problem. It works also with textureless objects, as you see here, and despite even occlusions, and the objects can be self-similar. There's a competition on this problem where this algorithm did very well, which was run now 2 years ago. And what's interesting that even this was only using RGB input images, it performs as well as if you have also the depth input, if you have depth sensing capabilities. And what I want to just sort of show you in the 1 or 2 minutes is some of the more recent results. One can apply similar method to articulated objects. So we are estimating here, given individual frames of the video, not only the pose of the robot, but also its articulation. So this is more degrees of freedom. We are expanding the space. It's not just 6-dimensional translation and rotation of the robot, but in additional articulation. And one of the very recent results which just got accepted to Robot Learning Conference, Coral, is that which you've seen so far, we require the model to be known in advance. So at training time, the method needs to know the models and it learns on them, and it can still take quite a lot of time. This is a step, is a new approach which does not require the models to be known at training time. So in fact, we have a large data set of more than 1 million images, 50,000 different scenes, where you have many different objects from a database of CAD models. And we learn a model, a deep neural network, which can then align new objects never seen at training. So this is really a step addressing one of the key limitations. We are very excited about this. So we have, at training, you synthesize this large number of images from a large database of CAD models. And at training, you see a new model here, the scissors, and you can estimate its accurate 3D pose in the image so that then the robot can go in and grab the object. And it does work. You can simulate these effects like occlusion and the variability of objects. So these are some of the examples from the test set, and it has never seen this object at training time. And so what you can do now, you can estimate in the video, you can estimate the pose of an object which you haven't seen at training time. And so now if a robot can come in and start manipulating these objects, and it's maybe somewhere later in the video. So I will finish with this. So we are very excited about learning from instructional videos and are also working on these different steps, both extracting these video language models, extracting more physics-based representation so that we can really interact and manipulate the world around us. Beginning to work on transferring these skills onto robots, which is very exciting, and also closing the loop with the perception. I thank you very much for your attention.
Is it working? Yes. Sorry. So thanks. It's been an impressive completion of your talk. So, but all the references are there for interested people. But yet, owing to this effort, we can take a few questions now.
Yeah, apologies for being fast, but I wanted to save some time for the coffee break. Yes, please.
So at some point you had some training using the images from, and you said it's not possible to do everything by reinforcement learning, and I didn't get exactly why, because you have this simulated environment, and it seems to be quite relatively constrained, and I thought you could maybe explore all the possibilities there. I'm not sure. How much does it speed up?
Yeah, it's a very interesting point. So one would think, we also thought, oh, this is going to be easy. We're going to do by RL, we'll solve our problem. But it turns out, so here the RL needs to work it really operates in the joint space of the robot. So this is, first of all, is not an easy space to operate in, because it's, really what you're controlling are particle angles and velocities of the robots, which has maybe 7 degrees of freedom. In addition, you're optimizing the position of these objects in the scene. So the space turns out to be somewhat high dimensional, and the standard RL techniques are just not able to find a reasonable solution. So we devise, and I did skip the details, but what we combine is that we combine here sort of more standard optimization techniques, which are, so first we find a trajectory of the tool, which is easier because it's just, three-dimensional, and use the video to help to guide the process, because we have the trajectory from the video, and then use more standard optimization techniques to find, from robotics, trajectory optimization, to find the joint angles, and use those to steer the reinforcement learning, if you wish. But you are also surprised, the reinforcement learning is not a magic bullet. Some of these problems are still hard search problems. Yeah.
Another question? Nope. Then I'll ask one.
Okay.
So, when I was in the movie industry, people were all excited about doing animation through mocap. So you reanimate a creature, which can also be of a different type of morphology, etc. So, can you see any applications in this field of content creation, whether it's for games or movies or whatever?
Yeah, definitely. I think it's interesting. So some of the tools in robotics, and Nicola can say more about this, are also used in graphics. What's interesting, though, is that when we started to talk with roboticists like Nicola, it's that you can't really easily transport from the graphics to robotics, because when you have a real robot, you have to really, and Nicola talked about it, respect the constraints. And whereas for animation, the problem is that it has to look good, and whether you are the model is actually using forces which are unreasonable, like much more what a human could do, doesn't matter that much. So in some sense, I would say yes, and maybe the problem is easier because you don't have to respect the real-world constraints. But of course, it's a very nice application area as well. Yeah.
The session, and you can ask over the coffee break, I'm sure. So thanks again, and I will pass the mic to the organizers.